We can definitely travel into the future by moving faster relative to everybody else.
Right now, as you're watching this video, you're traveling through time at exactly 1 second per second.
Time travel is entirely allowed.
But if you were moving fast enough, you could travel into the future. If you could move faster than light, you might travel into the past. And if you tried to change history, you might accidentally erase yourself from existence.
Because if you go back and prevent your parents from meeting each other, then you will never be born.
These aren't science fiction fantasies. They're real predictions from Einstein's equations that have been proven in laboratories and observed in space. And they create paradoxes so mind-bending that physicists are still arguing about them over a century later. Welcome to the universe where time itself becomes your enemy, where traveling to the past might be impossible for the strangest reason imaginable, and where the very act of observing reality literally changes what exists. Every time you use GPS to navigate, you're witnessing one of the most mind-bending paradoxes in physics. The satellites orbiting above your head are living in a slightly different flow of time than you are. Einstein's theory of relativity predicts that time runs faster in weaker gravitational fields. Since GPS satellites orbit 12,000 miles above Earth, where gravity is weaker, their atomic clocks tick faster than identical clocks on the ground, about 38 microseconds faster every single day. That might sound trivial, but GPS needs to know your location within a few feet. If engineers didn't constantly correct for this time difference, your GPS would be off by about 6 miles after just 1 day. Your phone literally has to account for Einstein's predictions about space and time just to tell you where the nearest coffee shop is. But gravitational time dilation is just the beginning. If you could travel at 90% the speed of light for what feels like 1 year to you, you'd return to Earth to find that 2.3 years had passed for everyone else. Travel at 99% light speed for a year, and you'd come back to find that 7 years had gone by on Earth. This creates what's called the twin paradox. Imagine identical twins, where one stays on Earth and the other travels to a nearby star at near light speed. When the traveling twin returns, they would be significantly younger than their Earth-bound sibling, not just in appearance, but literally in biological age. We've actually observed this effect with subatomic particles called muons, created when cosmic rays hit Earth's atmosphere. These particles normally decay in just 2.2 microseconds, far too quickly to reach the ground from the upper atmosphere. But because they're moving at nearly the speed of light, time dilation allows them to survive long enough to be detected at sea level. From the muon's perspective, the journey takes the expected 2.2 microseconds. But from our perspective, the muon's internal clock is running so slowly that it survives the much longer trip to Earth's surface. Einstein's equations don't just allow time travel to the future, they actually permit travel to the past under certain extreme conditions. Rotating black holes, cosmic strings, and traversable wormholes could theoretically create what physicists call closed time-like curves, paths through space-time that loop back to earlier moments. But here's where physics gets weird. The moment time travel to the past becomes possible, paradoxes emerge that might make it impossible. The most famous is the grandfather paradox. Imagine you travel back in time and accidentally prevent your grandparents from meeting. If they never meet, your parents are never born. If your parents are never born, you're never born. But if you're never born, you can't travel back in time to prevent your grandparents from meeting in the first place. This creates a logical contradiction that has no resolution within a single timeline. Either the past cannot be changed, or changing the past creates new alternate timelines, or time travel to the past is simply impossible. An even stranger paradox is called the bootstrap paradox, where information or objects exist without any point of origin. Imagine you travel back in time and give Shakespeare a copy of Hamlet. Shakespeare then publishes it as his own work. Centuries later, you buy a copy of this published version and take it back in time to give to Shakespeare. Where did Hamlet actually come from? You didn't write it. You just copied it from Shakespeare. But Shakespeare didn't write it either. He copied it from you. The play exists in a closed loop with no actual origin point. Some physicists propose that these paradoxes resolve themselves through the many worlds interpretation. If you traveled back to prevent World War II, you wouldn't change your own timeline. You'd create a new branch of reality where the war never happened. Your original timeline would continue to exist unchanged, but you'd now be stuck in an alternate version of history. This means time travel might be possible, but it could never change your own past. You could only create new alternate futures branching off from the moment you arrive. But time isn't the only thing that behaves strangely in our universe. Reality itself changes depending on whether anyone is watching. In 1801, physicist Thomas Young discovered that light behaves like a wave when no one is looking, but like a particle when someone tries to observe it. This led to one of the most famous thought experiments in physics, Schrödinger's cat. Imagine a cat in a sealed box with a radioactive atom that has a 50% chance of decaying within an hour. If the atom decays, it triggers a device that releases poison, killing the cat. If it doesn't decay, the cat lives. According to quantum mechanics, until someone opens the box to check, the atom exists in a superposition of both decayed and not decayed states. This means the cat would simultaneously be both alive and dead until the moment of observation collapses the quantum possibilities into a single reality. The act of measurement doesn't just reveal what happened, it actually determines what happens. Reality remains fuzzy and undefined until consciousness forces it to choose. We can demonstrate this with the famous double-slit experiment. When you fire individual photons through two parallel slits, they create an interference pattern on a detector screen, proving that each photon somehow goes through both slits simultaneously. But the moment you place a detector at either slit to see which path the photon takes, the interference pattern disappears. The photon suddenly behaves like a normal particle, choosing one slit or the other. It's as if the photon knows whether it's being watched and changes its behavior accordingly. The universe appears to be fundamentally uncertain until someone forces it to make a decision. This brings us to perhaps the most unsettling paradox of all. If the universe is so vast and old, where is everybody? The Fermi paradox asks why we haven't encountered any evidence of alien civilizations despite the enormous size and age of the universe. Our galaxy contains over 100 billion stars, many with planetary systems that could support life. The universe has existed for 13.8 billion years, more than enough time for civilizations to arise, develop technology, and spread throughout the galaxy. Astronomer Frank Drake created an equation to estimate how many communicating civilizations might exist in our galaxy. Even with conservative estimates, the numbers suggest there should be thousands or millions of detectable alien civilizations. We've now confirmed over 6,000 exoplanets, with billions more likely existing throughout the galaxy. Statistical analysis suggests that rocky planets in habitable zones around sun-like stars are extremely common. Yet after decades of searching with increasingly sophisticated radio telescopes, we've detected nothing. No artificial signals, no signs of massive engineering projects, no evidence that intelligence has ever existed anywhere else in the observable universe. This silence is so profound that it suggests something fundamental about the nature of life, intelligence, or the universe itself that we don't understand. Some scientists propose the Great Filter, a catastrophic event or impossible transition that prevents most life from evolving into spacefaring civilizations. This filter could be behind us, explaining why life is so rare. Or it could be ahead of us, suggesting that advanced civilizations inevitably destroy themselves. If the filter is ahead of us, it means that despite all our technological progress, we're approaching some fundamental barrier that no civilization has ever successfully crossed. Alternatively, the zoo hypothesis suggests that advanced aliens exist but deliberately avoid contact, treating our solar system like a nature preserve where primitive species are allowed to develop naturally without interference. Or perhaps we're living in a cosmic simulation created by advanced beings, and they simply haven't programmed any other intelligent life into our local region of the simulated universe. But the strangest paradoxes might exist at the edges of black holes, where time, space, and information itself break down in impossible ways. If you fell toward a black hole, tidal forces would stretch your body like spaghetti long before you reach the event horizon. But from your perspective, the fall would seem to take a finite amount of time, and you'd cross the event horizon and continue falling toward the center. From an outside observer's perspective, however, you would appear to slow down and freeze at the event horizon, your image gradually fading and redshifting until it disappears. To them, you never actually cross the boundary. You remain stuck at the edge forever. This creates the information paradox. If information falling into a black hole is destroyed when the black hole evaporates through Hawking radiation, it violates quantum mechanics. But if the information escapes somehow, it contradicts general relativity. Recent research suggests that information might be encoded in correlations between Hawking radiation particles in ways so complex that it's effectively impossible to reconstruct what fell in, even though the information technically survives. These paradoxes reveal something profound about the nature of reality. The universe operates according to rules so strange that our everyday intuition simply cannot comprehend them. Time is not constant, but flexible. Reality is not fixed, but depends on observation. Information cannot be destroyed, but can be scrambled beyond recognition. The past might be unchangeable, or it might branch into infinite alternate histories. Perhaps the greatest paradox is that we exist at all in a universe governed by such bizarre rules. The fact that conscious beings evolved capable of discovering these paradoxes might itself be the most improbable thing that has ever happened. We are living contradictions in a paradoxical universe, using minds that evolved to hunt and gather on African savannas, to contemplate the deepest mysteries of space and time. Every time we think we've figured out how reality works, the universe reveals new impossibilities that force us to question everything we thought we knew. The paradoxes aren't flaws in our understanding. They're glimpses of a reality so strange and wonderful that it exceeds the boundaries of human logic. And perhaps that's the most beautiful paradox of all. In a universe that makes no sense, somehow, miraculously, we do. The fact that you can understand these paradoxes, even if you can't resolve them, means you're participating in the universe's attempt to understand itself. And that might be the most profound mystery of all, that the cosmos created beings capable of contemplating their own cosmic insignificance and finding it absolutely fascinating.